Yes, Doc, we can start.
So because yesterday you couldn't hear me too clearly, I'll try and recap quickly what we started yesterday. Okay. All right. So this is so damn slow. All right. So I was saying yesterday that ultrasound. The word ultrasound basically means that ultra has to do with very high, all right? So when we talk of ultrasound, they are basically sounds with very high frequencies, okay? So usually the ones, what we refer to as ultrasound or sound that is in the ultra high range is one that has a frequency of between 20,000 to 1 million hertz. That is cycles per second, that's a unit, or more than that. And when we are in medical sonography, the ultrasound waves that we use have a frequency ranging from 3.5 to 10 million hertz thereabout. That's what we use in medicine. And this is quickly a picture of an ultrasound scan machine. And
hello, Doc.
Yes.
Please, there's a prompt on your screen that you may have to press OK. It seems to be obstructing us.
Me, I press OK. Can you guys see that? But I can't see. Let me see. Yes, I thought my screen.
Where?
Okay, no, it's okay now.
The thing is gone.
Yes, Doc.
Okay. Now, so what I was saying was that now ultrasound waves that we use in ultrasonography are basically the ultrasound material, okay, is put in the transducer, the probe. I'm sure you've all seen an ultrasound scan machine before. So the probe that we put on the patient has the ultrasound material inside. Okay, there are different types of materials, but the ones we use are largely ceramic materials. So they're in the probe. And what happens is that the electric current is passed through these ceramic materials, and then they vibrate at a very high frequency. And what happens is that it generates sound waves. So these sound waves are channeled through whatever it is that we are studying. And then the returning waves that are reflected coming back to the ultrasound material is received and then changed into electric current. And that is what is translated on a computer screen for us to see as images. Now, when ultrasound goes through matter, there are a number of things that can happen. One, the sound waves can be reflected. Two, they can be refracted, they can be diffracted, or they can be attenuated or scattered. And they are ultrasound because we cannot hear, the human ear cannot hear these sound waves, okay? But there are certain animals that can hear sounds with these at these frequencies. Okay. Right. So ultrasound waves are usually produced by the piezoelectric crystal. That's the ultrasound materials. That's what they are called. They are piezo. I mean, the principle on which they operate in physics is referred to as the piezoelectric principle. So the crystals that do this are the piezoelectric crystals. Okay. And so as I was saying, I think there's just an explanation of what I've said already. So when you pass electricity through the waves, as is done with the probe, it causes it to vibrate, and that causes to produce the waves that are shot out of the probe and then into the matter, and then reflected back. Okay, so the most common ones are PZT and PVDF. That is the Dinkesi. polyvinylidene fluoride. There are so many others, but these are the common ones that we use most of the time. Okay, now also to note, so now we're going to take some of the principles one by one. Now, first thing you need to note is that the thickness of the crystal would determine the frequency of the sound waves that are produced from the scan head. And low frequencies, as I already said, are 3 megahertz, and high frequencies are in the range of about 10 megahertz. Now, what is the relation between the frequency of ultrasound waves and their ability to penetrate, or their penetrability? These are kind of MCQ things, okay? So when an ultrasound wave is of a higher frequency, then it means that it will have a shorter wavelength. This is physics. It will have a shorter wavelength, and therefore, because it has a shorter wavelength, it will penetrate less. So it will have a shorter penetration. However, it will have a good resolution. Okay? So this slide here, I can twist it in so many ways to test your understanding of what I'm saying. So a high frequency wave will have a short wavelength, and therefore it can penetrate deep into tissues, or into very deep tissues. However, it will have good resolution. And it's the opposite that is true for low frequency sound waves. So low frequency wave that is like 3 megahertz, for instance, will have a longer wavelength and have a longer penetration, however, may have poor resolution. I hope that is clear. So this is one relation you should note between the frequency of the ultrasound waves and their ability to penetrate, right? Now, then also let's look at the frequency and the resolution. Okay. Now, okay, so the higher the frequency, then oh, this slide. No, let's take this slide out. But as I was saying, if you have a higher frequency, hold on. Quiet. Sorry. So as I was saying, when you have a higher frequency, you have. Can you hear me, or there's a lot of interference?
Hello? Oh, Doc, this is fine. It's just we had kids in the background, but that's fine.
Sorry about that. Okay, so you have a higher frequency, you have shorter wavelength, shorter penetration, but good resolution. Okay, so that is what we are relating here as high frequency equals to a higher resolution. So if you look at the 3.5 megahertz probe here, okay, so you can see that the matter that is being shown here is not as clearly defined as you'd have in this one. So you can see that this one is showing us a better resolution compared to this. All right, and that is because this one has a higher frequency. Okay, so higher frequency equals higher resolution. All right. Okay, so basically ultrasonography has to do with it's a diagnostic imaging modality that is based on using ultrasound waves to study internal structures and or internal body structures, okay, based on just ultrasound. So their sounds are very high. Now, so right from there, we'll go to the main imaging modalities that ultrasounds give us. Now, ultrasounds give us grayscale imaging, then Doppler imaging, okay? Grayscale imaging, Doppler imaging. All right, now there are 3D, 4D, and the rest, but we wouldn't talk, we won't talk about that in this lecture. Okay. Okay. All right. So for grayscale imaging, we have three main types. We have the A mode. Now, this is especially for the grayscale aspect. You see them on most ultrasound machines. So you can take note of this so that when you see the keys on any ultrasound machine, you'll be able to have a fair idea what it is likely to be used for. Okay, so this has very important clinical applications. So let's keep this in mind. So grayscale imaging, we have three main types: A mode, B mode, M mode. Yeah, and then the Doppler imaging, we have continuous wave Doppler, we have the power Doppler, we have the color Doppler, we have the duplex Doppler, we have the pulse wave Doppler. So we are going to take the grayscale imaging, the three of them, we're going to take them one by one and go through. And then we will take the Doppler imaging one by one and quickly run through them. Okay. All right. So A mode. So this is the simplest form of ultrasound imaging, which is based on which is based on the pulse echo principle. Now, A scans can be used to measure distances. So when you see A mode on any ultrasound scan machine, know that this one we use it to measure distances, okay? And they only give a one-dimensional information. Because of that, they are not very useful for imaging. So we can use them in echocardiography, echo ophthalmology, when we need to measure distances, between various structures. Okay, A mode is very accurate. So A mode on the ultrasound scan is most appropriate for A, imaging, B, calculating distances, blah 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 blah. Easy question, isn't it? All right. Now, B mode. Yes. So B stands for brightness, whereas M stands for motion. Okay, so B, brightness mode. So B stands for brightness. So B scans are an improvement from A scans in that they're able to give a two-dimensional view as compared to the A mode that gives a one-dimensional view. Okay, so that is so for any cross-section or wherever you put the probe, whatever information you'll be seeing on a B mode is a two-dimensional. Okay, right. Now, it's generally used to measure the cardiac chamber dimensions, so that this is where you are able to add another dimension to be able to get volumes. Okay, so you measure about three width, depth, and height to be able to get volume. So typically, if you see a cardiologist using an ultrasound to calculate heart chambers and the rest, they are likely to be using the B mode. So take note of that. So general use are chambers, valvular function and structure, etc. Right. Now M mode. So M stands for motion. So this represents movement of structures over time. So M mode is commonly used for measuring chamber dimensions, and it's more so it's also applicable in the same echo. Okay, and it looks just like recording a video in ultrasound. So with that one, you'd actually see the movement of the structures. If they are moving, you could see the structures moving in there. So that is the M mode. All right. So that's for the grayscale imaging. Those are the first three, the grayscale imaging, the three dimensions, A, B, and M. Right. Okay, so we have 2 minutes left. We'll quickly take this one and then continue after the reload. So Doppler imaging. So it's a general term used to visualize velocities of moving tissues. So with Doppler, the advantage that we get from Doppler is that we're able to measure the speed at which various structures are moving, for instance, particularly blood flow, okay, or fluid. And that is able to tell us whether there's likely to be blood, there's likely to be ascites, there's likely to be pus, blah, 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 whether it is a blood clot, DVT and the rest. Doppler helps us. Okay, so it gives us the speed for us to be able to know, because we know the speed at which various structures should be moving. So Doppler ultrasound evaluates blood velocity as it flows through a blood vessel. Blood flow through the heart and blood vessels has certain characteristics that can be measured using Doppler instruments. So as I said, we know the standard speeds and the rest. So when we measure them, we're able to tell that this is blood, this is venous blood, this is arterial blood, and so on. Okay. And other things that also help us that if you have a normally open vessel, there's what you call laminar flow, where the blood that is closer to the vessel walls are flowing at a slower speed than those that are in the middle. So that is what is being shown on the laminar flow there. However, whenever there's any form of obstruction or there's any little occlusion of any vessel, the flow immediately behind that obstruction becomes turbulent before it eventually gets back to its laminar flow upstream. Okay, so that is what this picture is showing. So, and that these are some of the things that the ultrasound can detect for us to know whether there's a thrombus in the vessel or something like that. Okay, so look at the four main types of Doppler ultrasound: the continuous wave Doppler, pulse wave Doppler, color Doppler, power Doppler.
Hello, Doc.
Yes. Okay, so after the break. So yes, quickly log on. Let's not waste time. When you right afterwards, everybody should log on quickly.
All right, Doc.